Okay, so we've done a little bit of graphing. We've talked about the 10 basic functions. Today we're going to talk about, hopefully remind you of, not teach you for the first time, but we'll see how it goes, about transformations and how if you recognize transformations and you know the 10 basic functions, it's really easy to graph by hand, which is why your homework is on paper today and not on Math Excel, because all the ones on Math Excel were multiple choice, pick the right graph. Homework is not going to be, your test is not going to be multiple choice, pick the right graph, so I'm making you graph by hand today. But using transformations, graphing becomes much easier and less tedious and fun, we should say. All right, so horizontal and vertical shifts, moving it left and right and up and down. It's all about adding or subtracting a number either inside the function or outside the function. So I wrote it like as a function, and then I'll give you an example. So if we want to shift a graph up, I said graph, you just take the function and you add a number to the outside. So an example of that would be like f of x equals the absolute value of x plus 5. Sean, what do you expect? What? Oh, I said in my 5th hour class yesterday, like they just never stopped talking. It's like a full class, like every day. And I said, I wish I had a little button that I could push it, and it would just give you a little shock just to get your attention. They're like, ooh, that's abuse. And I was like, it's not really abuse, just a little shock. Just a little tiny shock. Just to be like, hey, I said we're talking. No, I'm If we are shifting a graph down, we just subtract a number on the outside. So that's like x squared minus 2. Notice the number is away from the function, added or subtracted on the outside. Yes? The lava, me talking about electrocuting students. Yeah. Could use that against me in a court of law. Only no one ever watches the videos, so it's okay. Keep them at absent. They're supposed to be for absent children. Left and right means you're going to add or subtract inside the function, but it's the opposite of what you would think. If you're moving something to the right, you actually subtract the number. So that would be like if I said parenthesis x minus 2 squared. If the minus 2 is inside the square, that means I'm moving it to the right 2 units. And if I'm moving it to the left, it's actually adding it inside the function. So that would be like, that would be like parenthesis x minus 5 cubed. That would be that little like S graph. But minus, no, I did it up backwards. Plus 5 would be moving it to the left. I'm sorry. I heard that. He said, I'm not sorry. So, the idea is you know those basic graphs or the parent graphs, and then if you see this, all you do is move it left, right, up, or down, and then you don't have to make an XY chart, and you don't have to stress, and you don't have to cheat and do it on the graphing calculator, right? I don't even have a invisible. So it says use the graph of x squared to graph the following, meaning that they hope that you know what x squared looks like. And so I'm going to graph both of them. I'm going to graph x squared, and then I'm going to graph the other one. If you don't want to graph both on your paper, you don't have to. But I'm going to graph both and then show you that's what just moving it. Left, right, up, down. So first of all, if I'm subtracting 3 on the outside, what am I doing? It's on the outside of the function. Look back at the notes that we just wrote out. Right, if it's outside the function, this means that it's moving down 3 units. Okay, so I'm going to graph x squared, f of x first. You should know x squared starts at 0, 0. And then if you plug 1 in, you get 1. You plug -1 in, you get 1. Right? If you plug 2 in there, you get 4. So if you go over 2, you can go up 4. And that works the same way over here, over 2, up 4. And you get that lovely parabola shape. No, I food at all. So, if I'm moving it down 3, if you had a magic smartboard at your fingertips here, you're really just taking this graph and you're moving it down 3 units. Like, it should look exactly the same. Forget the part I said up here. But what I do when I don't have a smartboard at my fingertips, I know that vertex normally is at 0, 0. I just move it down 3. And then I don't pick an XY chart. I know if I go over 1, I should go up 1, right? And if I go over 2, I should go up 4. It's the same idea, just moved down 3. So, think about when you do a shift, whether your domain and range would change here, right? So normally x squared has a domain of all real numbers, but a range of 0 to infinity. On this new graph, is the domain going to stay the same? It's still all real numbers. But is the range going to stay the same? No, because I moved it down 3. So now instead of starting at 0, it's going to start at -3, 2. So what about this one? What's happening if we have a +2 on the inside and a +1 on the outside? And I always use that vertex as like my moving point. So normally, I won't graph the x squared on this one, but normally I know it starts at 0, 0. So if I go left 2 and up 1, I know that's my new vertex, and I don't have to make an XY chart. You follow me on that? And then if I go over 1, I go up 1. If I go over 1, I go up 1. If I go over 2, I go up 1, 2, 3, 4. 2, 3, 4. And I have a pretty accurate graph without having to do much work. So what's the domain on this? Savannah, what's the range on this? So, which number determines your range? Like the number on the inside or the number on the outside? Because the outside is moving it up and down. So if there's nothing added or subtracted on the outside, your range, did I say domain? I don't know what I said. But your range will start at 0 unless there's something added or subtracted on the outside. So I want to talk about reflections in graphs, and you've been doing this since Algebra 1 because when you talked about parabolas, you knew positive x squared opens up and negative x squared opens down. But that's true for any graph. And so if you reflect your graph in the x-axis, it means like you're changing the function, the whole side of the function. So I wrote here, that means your y values change. So for every x value that's the same, your y values change and it would flip over. I always remember the negative is outside the function. So if the negative is outside the function, then I haven't changed the x values, but I'm going to be changing the y value. So that's going to flip over. So, I'm not going to get very points here, but for absolute value of x, what kind of graph does that look like again? A V-shaped graph, right? It's always positive. So it's like a parabola, except for it's a V-shaped graph. This is why equals absolute value of x. If I ask you to graph negative absolute value of x, I can still pick all the same x values, 0, 1, 2, 3. But now I'm going to get all negative y values. So that's why that when you put the negative on the outside, it's going to flip over the x-axis. Reflection in the y-axis is if you put a negative inside the function. And for some equations, putting a negative inside the function doesn't change anything. Like think of x squared. If I asked you to graph y equals x squared and y equals negative x where the negative's on the inside, right? Like that's the same graph because it doesn't matter when you square it, it's still always positive. So if it's already symmetric with the y-axis, putting a negative inside doesn't change it. But if it's not already like that, then that means your x values are going to change, which means it's going to flip over the y-axis. So negative on the outside is over the x-axis, negative on the inside is over the y-axis. And I kind of put a double one here of, this one's already the normal square root of graph up to. This one's also up to, but I put a negative on the inside. So think about, this might be one if you don't know what it normally looks like, that you might pick some points here. To me, a square root graph is like that half of a parabola that goes out from 0 normally. But because I put +2 here, it's actually going to go up 2. So if I was going to graph this, I'll actually make some things. Normally, I just say at 0, we start at 0, but we actually moved that up 2. Now we have 0 plus 2, so it actually starts up here at 2. If I plugged 1 in there, normally the square root graph, if I plug in 1 to get 1, we have to add 2 to that, right? So at 0, I get 2. At 1, I get 1 plus 2, which is 3. Be another good 4, if the square root of 4 is 2, but 2 plus 2 is 4. So at 4, I actually get 4. So I get that little half of a parabola. It's a curve going out like this. If you put a negative under there, like your domain changes, because I could still pick 0 and I could still get 2, but I couldn't pick 1 now because I can't take the square root of negative 1 and graph it. So you have to pick negative x values. So that's what makes it change and flip over. So now you would pick like -1 and you would get 3. And you would pick -4 and you would get 4. So it just flips over. So I get those same points. So negative on the outside, flips it over the x-axis, negative on the inside, and the other thing that I want to talk about, oh wait, do I have graphs of this to do? The other thing I want to talk about is what happens when you stretch and you shrink that graph. So everything we did so far, moving it left and right or flipping it over, we haven't actually changed the shape of the graph. So we can use those parent graphs and we're just like sliding it around or flipping it. We call those rigid transformations because everything stays the same. And we can also talk about stretching and shrinking the graph, and they call those non-rigid transformations. And you can stretch your graph vertically or you can shrink it vertically. You can also stretch it horizontally, and it's all about whether you multiply a number on the inside or on the outside. And I'll tell you that your precalculus book says it a little different than the algebra 2 book, so it's a little bit iffy. But so if you have a vertical stretch, the big thing, whoa, that's not really what oh my gosh. There we go. A vertical stretch. C is a number that you multiply by the function. So the big thing about a vertical stretch is you're multiplying that number on the outside of the function. Whether it's a stretch or a shrink, sometimes they call it a stretch or a compression. If C is bigger than 1, it's going to stretch that out. So like the parabola might look like really thin. If C is less than 1, and by less than 1 I don't mean a negative number, because negative is a reflection, I mean like a fraction, right? So it's like between 0 and 1. So if it's like 1/2 or 1/4, it's going to actually shrink that graph down. So it's going to take that parabola and like squish it down, and it's a little wider. Horizontal stretch. The Algebra 2 book talks about multiplying the number and flipping it over, but this book is kind of crazy with the way that it does it. But basically, it's on the inside, but notice they write it as a fraction. So they say f of x over c, and if it's bigger than 1, they say that's a stretch, and if it's less than 1, they say that that is a shrink. And I'm going to give an example of this applied. I'm not going to make you say horizontal stretch or horizontal shrink that much. I do kind of want you to know the difference between horizontal and vertical. Vertical is on the outside, horizontal is on the inside, and then if you're not sure whether it's a difference, you have to okay with that. So this is multiplying on the inside of the function. So up here, that would be like y equals 3 times x squared, right? The 3 is not in the squared part. It was not like parentheses 3x squared. That would be stretching it by a factor of 3. Down here, because they put c in the bottom, it's a little tricky. So think about if c were 2. You would like have f of x over 2. So think about if it was x squared. It would be like saying x squared is like x over 2 squared. So c is really bigger than 1, because 2 is bigger than 1. But when you look at this problem, like to me, I always think of that as a half, and so I always think that that's smaller than 1, so I get confused by it. But c is technically bigger than 1, so a horizontal stretch is when you actually end up with kind of like a fraction in there. And a horizontal shrink would be like, think about if you divided by a fraction. If I had y equals x over 1/2 squared, your book's never going to leave it as x over 1/2 squared, because that's the same as 2x squared, right? Because dividing by 1/2 is the same as 2. So just trying to tell you that if you're trying to identify whether it's a stretch or a shrink, or horizontal, your book does it a weird way. In the Algebra 2 book, we said it's a horizontal stretch if this were less than 1, it's a horizontal shrink if this were greater than 1, and then we don't have to remember the fraction. Don't stress a lot about that. I don't really care that you have all that memorized, but I just wanted to explain it to you the way the book's going to explain it to you as you practice these functions. The big thing I want you to know is when the 2 is on the inside of the function, it's horizontal going to change. If the number's on the outside of the function, it's going to change vertically. And this is where maybe you just have to make that correction to help you out a little bit. So let's graph. Look, I did both on the outside. So 2 times the absolute value of x means that that's a vertical stretch, stretching it by a factor of 2. So this is going to change the shape of our graph. And again, I'm going to graph both on this first one at least, so you can kind of see how it changes. Maybe you can come up with a little shortcut to help you a little bit. So if I just graph absolute value of x, that's where it starts at 0, 0, and at 1 I get 1, at 2 I get 2, at 3 I get 3. And absolute value is always positive, so at negative 1 I get 1, at negative 2 I get 2, and negative 3 I get 3. If I stretch that by a factor of 2, I'm just multiplying all those numbers by 2. So 2 times 0 is still 0. But now when I plug 1 in there, I'm actually going to get 2. When I plug -1 in there, I'm actually going to get 2. When I plug 2 in there, I'm going to get 4, because I'm just multiplying it by 2. So basically, I'm making it like twice as big, right? Like I'm stretching it out. You're not taking that and stretching it out. If there was a 5 in front of that, like it would be super stretched out, because at 1 it would go all the way up to 5. And so again, if you know the parent graph and there's not a whole lot of stuff going on in the problem, just to stretch or shrink, you can just multiply all your normal answers by the number out there. On a stretch or shrink on this one, is the domain and range going to change? Okay, domain's still all real numbers, range is still... This one I threw a negative up there, and I put a fraction there. The negative, remember, is a reflection, right? And a negative on the outside is reflecting it down, right? So this should be reflecting over the x-axis, and this is a vertical shrink. So, where when I teach algebra 2, even when I taught algebra 1, I always told kids when you're graphing, like, always take like -1, 0, and 1. They're great points to pick. The exception to that rule is when there's a fraction in there. I would never pick -1, 0, and 1. When there's a fraction, I always try to pick numbers that make that work out nicely. So if I was going to, and I'm just going to pick some points to show you probably what I did, so I tried, but that's okay. 0 is still a great point to pick here, because that's still going to be 0. We're just flipping it over. Normally, when I plug 1 in there, I get 1. The negative means it needs to go down, but by stretching it or shrinking it vertically, normally we only have to go over 1 to go down 1. But now that's only 1/3 of that. So now, one way to think about it is you have to go 3 to go down that normal 1. Or think about what number could I plug in there that's going to divide out nicely. If I plug 3 in there, I'm going to get -1. Negative because it's flipped. So that's the way that you can think about stretching it. You're going twice. So every 1 you're going up 2. If you're shrinking it, now you have to go 3 times as much to go down that same distance. So that's one way that it helps to think about it. And how far would I have to go over before I could go down 2? 6, which isn't even on my graph, but like I would have to go way down here. So it's definitely a lot wider. Right? Another thing that's supposed to help you by doing this is if you know that it's going to be shrunk or compressed, you know what your graph should look like. So if you did something wrong, you should be like, that graph doesn't look right. I need to change what I did there. Domain and range on this one change? Right. The domain's still in -infinity to infinity, but the range now, instead of going up, is going down. So the range would be -infinity up to 0 on that. So what I did for you is I made you some lovely graphs. This domain. So the first 6, and I know the bottom graphs probably so well, sorry about that. But the first 6, like there's 3 quadratic transformations, and there's 3 active values of the transformation. And you need to think about what stage. Number 3 is really accurate. I put it in next to the way so that it's equal. I do want you to think about anything with numbers, right? And then on the back, I just have 2 questions where I told you the transformation and I want you to write the If you have questions on other homework, I can answer them now.